4.3 vertical and horizontal asymptotes. So when we add, subtract, or multiply two polynomials, we get another polynomial function. However, dividing two polynomials does not yield a polynomial function. What that's going to be is a rational function, okay? Because it's going to be some p at x over some q at x function, so it's going to be rational. Okay, so just to recall, rational functions have such features as vertical and horizontal asymptotes. Okay, so for vertical asymptotes and rational functions, we're going to recall the notation as x approaches c from the positive side or the right side, and x approaches c from the negative side or the left side. Okay, and when we evaluate functions as x approaches c from either side, so from the left or from the right, we know that as values get increasingly large and positive, the values approach infinity. And as values get increasingly large and negative, the values approach negative infinity. And since the symbol infinity, which is the symbol right here, is not a number, the limits the limit as of 1 over x minus c as x approaches c from the positive side, and the limit of 1 over x minus c as x approaches c from the negative side do not exist, right? Because if we substituted essentially c in here, c minus c is 0, we're going to kind of get a 1 over 0. For simplicity, we use that the limit of these two, so the limit as we approach c from the positive side of this function, it will approach positive infinity, and from the left side, it'll approach negative infinity. And we're going to see that in these diagrams below. Okay, and as a recall, a rational function is in this form. So f at x equals p at x over q at x. Okay, it has a horizontal asymptote, x equals c, if when we plug in c to that x value in the denominator, p at c does equal 0. Sorry, I said p. Q at c equals 0, and then p at c does not equal 0. So essentially what this is saying is when we plug in some value of c, we're going to yield some number over 0. Therefore, because we get a 0 in the denominator, we have a vertical asymptote. Okay, so when we're actually assessing the vertical asymptotes, whether they are vertical asymptotes and where we approach from both the left and the right, we use here's vertical asymptotes and infinite limits. So the graph of f at x has a vertical asymptote at x equals c, so this is like c right here, this dotted line, if one of these statements is true. So as we approach, the limit as x approaches c from the left approaches infinity, or x approaches c from the left approaches negative infinity. Okay, the limit as x approaches c from the right approaches infinity, or the limit as x approaches c from the right approaches negative infinity. Okay, if any of these statements are true, then we have a vertical asymptote at c. Okay, example 1. Determine any vertical asymptotes of the function f at x equals x over x squared plus 2 or plus x minus 2, and describe the behavior of the graph of the function for values of x near those asymptotes. So step number 1, we have to determine when the function is undefined. So determine when f at x is undefined. Okay, so what we do is we take this denominator and we factor it. So what two numbers multiply to -2 and add to 1? Well, 2 and -1. Okay, so we get f at x equals x over x plus 2, x minus 1. So we're going to have a vertical asymptote at x equals -2, and we're going to have a vertical asymptote at x equals 1. Okay, so what we want to do is we want to check how this function approaches those vertical asymptotes. So we're going to check the vertical asymptote from the left and the right. Okay, so we're going to have, as x approaches, -2 from the left, and as x approaches, -2 from the right, and then x approaches 1 from the left, and as x approaches 1 from the right. Okay, so we're going to take each one of these, and we're going to assess at x plus 2, and then x minus 1. And then we're going to be able to say, okay, overall, what is f at x doing? And then overall, where does f at x approach? So as x approaches -2, from the left, -2 from the left is going to be -2.1. Okay, so if we sub in -2.1 to x, we get negative. 2.1 plus 2, we're still going to get negative. Negative minus anything is negative. So we're going to get a negative, and we're going to approach negative infinity. Okay, these two things go together. As x approaches -2 from the right, which is going to be -1.9. So this is negative 1.9 plus 2 will be positive. Negative minus anything is negative, so we get positive. So we're going to approach positive infinity. Okay, 1 from the left is going to be 0.9. Okay, so this is going to be positive. 0.9 plus anything is positive. 0.9 minus 1 is negative. Okay, so we're going to approach negative infinity for that one. And x approaches 1 from the right, so let's call that 1.1. Positive, 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 positive infinity. Okay, so when we sketch this and we have some vertical asymptote at x equals -2, and we have some vertical asymptote at x equals 1, we know on the left side of -2, we're going to approach from down here. On the right side of -2, we're going to approach from positive infinity. On the left side of 1, we're going to approach negative infinity. And on the right side of 1, we're going to approach positive infinity. Okay, so indeed, these two are asymptotes, and this is how we approach them. Okay, horizontal asymptotes and rational functions. The following notation is used to describe the behavior when a rational function, so as a recall, we have some rational function where we have a polynomial, maybe p at x in the numerator, and a polynomial, let's say q at x in the denominator. Okay? So as x increases without a bound, okay, in the positive and negative directions. So what ends up happening is as the limit, as x approaches infinity, okay, then obviously this is 2, 4, 6, this is going to be 8, 10, 12, all the way to infinity, okay, of f at x. The other notation is the limit of f at x as x approaches negative infinity. So again, -2, -4, -6, we could do like -8, -10, all the way to negative infinity. That's what that means. So this graph is one example. So the actual just reciprocal function, and when we say reciprocal function, we just mean the base one with no transformations. Okay, f at x equals 1 over x. How that would look like the limits for the reciprocal function is the limit of 1 over x as x approaches infinity equals 0. Okay, the limit equals 0, that means it's approaching 0. Okay, this is going to get closer and closer and closer to this number here. Okay, remember, we're talking about where it's approaching in regards to the y. And the limit as x approaches negative infinity of 1 over x equals 0. Okay, because this one is continuously approaching as well. We can also write each polynomial in a fraction function, so the term of the highest degree is a factor. I'm going to show you guys what that means. When we write polynomials this way, we can see that the value of x becomes large, either positive or negative, and the value of the second factor always approaches 1. Okay, so let's take a look at that. Okay, so write each function so the term of the highest degree is a factor by factoring out the leading coefficient. Okay, so if we have p at x equals x squared plus 6x plus 3, what this is going to look like is we're going to take the first term and we're going to divide each of these terms by x squared. Okay, so p at x is going to be equivalent to factoring out the x squared, okay, and x squared divided by x squared is just 1. 6x divided by x squared, the x and the squared on the x in the denominator go away, and we get 6 over x. And then 3 over x squared, we get 3 over x squared. Okay, and that's it. This is going to be the foundation for us finding horizontal asymptotes. So for b, q at x equals 3x squared plus 7x minus 5. We're going to factor out the full coefficient. So for each of these terms, we're going to factor out the 3x squared. Okay, so we're going to get the factor of 3x squared, and these two cancel out to a 1, plus 7x over 3x squared. The x and the squared cancel. We get 7 over 3x. And this stays as 5 over 3x squared. Okay, so going back up to this little blurb, the term of the highest degree is a factor. Okay, we made it a factor. Okay, and the value of the second factor always approaches 1. Okay, that's what it's going to look like. Okay, example 3, determine the value of each of the following. So we have the limit as x approaches infinity. So what we, of this function here, 5x minus 7 over x plus 1. So what we want to do here, as soon as we see the limit as x approaches positive infinity, we're thinking, is there a horizontal asymptote, or does it converge to an actual limit? Okay, so we want to use the skill that we just practiced, and we want to factor out a 5x out of the numerator. So if we have 5x minus 7, we want to go ahead and factor out a 5x out of both of these terms. And in the denominator, we have an x plus 1. What we want to do is we want to go ahead and factor out the x. Okay, so what we get is we get the factor of 5x, and we get 1 minus 7 over 5x. Divided by, we get a factor of x, and then we're left with 1 plus 1 over x. So we can cancel out this x and this x. Okay, so we're left with f at x equals 1 minus 7 over 5x over 1 plus 1 over x. Okay, this is just the function part. Now we want to find the limit as x approaches infinity. Okay, of f at x. So what we want to do is we want to sub in basically infinity. So we have 5 bracket 1 minus 7 over 5 times infinity over 1 plus 1 over infinity. Okay, so once we sub that in, we no longer have to write the limit, and we can calculate. So what I would start by doing is taking into account these infinities. So what is 7 over a really big number? Okay, any number over a really big number is going to tend to 0. Okay, and you can do this by doing in your calculator, like 7 divided by 9999. Okay, you're going to get a very, very, very small decimal. So that's going to tend to 0. Also, 1 over infinity is going to tend to 0. So 1 over, again, 999999, if you have to check it in your calculator, okay, it's going to be almost 0. So we interpret those as nothing, and we can say that the limit is 5, because we're going to have 5 times 1 minus 0 over 1 plus 0, which is just 5. Okay, what this means is that our graph of this rational function is going to approach, as we approach positive infinity, it's going to approach 5. We don't know if it's from the above or below, but it will approach 5 as the horizontal asymptote. So let's say horizontal asymptote x equals 5. Okay, next one. The limit as x approaches negative infinity of this function, x over x squared plus 8. So if we had the function x over x squared plus 8, we first want to divide the numerator by the leading coefficient, which is x, and the denominator by the leading coefficient, which is x squared. So we are going to get the factor of x, and then 1 is left in the bracket, and then we're going to get the factor of x squared, and then that cancels to a 1, and then 8 over x squared. That's going to be our new f at x. These two here are equivalent. All we did is factor. Okay, and at this point, we're going to go back to the limit as x approaches negative infinity. I'm going to rewrite it. I don't like what I did in the last one because I substituted in the infinity right away. But as soon as we substitute this infinity in, what happens is we no longer write the limit. Okay, so first I'm going to cancel this x and this squared. Okay, now I'm going to go ahead and sub in the limit as x approaches negative infinity. So 1 is in the numerator, that's just a constant. So for this x, sub in negative infinity. And then we have 1 plus 8 over negative infinity squared. Okay, what does this mean? So 8 over a really big number goes to 0. So this entire bracket's just 1, which we can essentially ignore. Like we can just cancel it out because anything times 1 is just 1. So essentially we have 1 over negative infinity. And if you were to put this into your calculator, even as 1 over negative 99999, okay, what you're going to see is that this is going to tend to 0. So the limit as x approaches negative infinity of this function here, there's going to be some horizontal asymptote at 0, and we're going to approach it from either above or below. So let's say the horizontal asymptote is x equals 0. Okay, to evaluate the following limit, we can divide the numerator and denominator by the highest power of x in the denominator. Okay, so I'm going to say that we're going to start with f at x equals, we have 2x squared plus 9. So let's go ahead and divide each by x squared. Oh, 2x squared to the full coefficient. Okay, and we have in the denominator 5x squared minus 8x minus 2, and we're going to divide each of these by 5x squared. Okay, so our function is going to be the factor 2x squared. I don't want to put that in a bracket. There we go. Okay, those cancel to a 1. Don't forget to put the 1 there. Plus, and then this one, nothing cancels. 9 over 2x squared. Then that's going to be over the factor 5x squared. Those two cancel to a 1. Minus 8x. No, this x is going to cancel with the squared. So minus 8 over 5x. And then this last term, minus 2 over 5x squared. Okay, and at this point, I'm seeing that there's a common x squared factor in both the numerator and the denominator. So now we have 2 over 5, 1 plus 9 over 2x squared, and then 1 minus 8 over 5x minus 2 over 5x squared. Now let's go back up here, and we are going to solve for the limit as x approaches infinity of 2 over 5. And we have 1 plus 9 over 2x squared, and then we have 1 minus 8 over 5x minus 2 over 5x squared. Okay, so that's the limit that we're solving for. So in the next step, we can go ahead and we can substitute in the infinity. So that gives us 1 plus 9 over 2 times infinity squared. And then we get 1 minus 8 over 5 times infinity minus 2 over 5 times infinity squared. And we know any number over infinity is going to tend to 0. It's going to be so small that it's insignificant. Okay, and now we have 2 over 5. Right? Because this bracket's just 1 plus 0, and this bracket's just 1 plus 0 plus 0. So we can say that the horizontal asymptote is x equals 2 over 5. When the limit as x approaches infinity of f at x equals k, or the limit of f at x as x approaches negative infinity equals k, the graph of the function is approaching the line y equals k, which is the horizontal asymptote of the function. Okay, we've already talked about this. In order to know whether the graph approaches the horizontal asymptote from above or below, we need to consider f at x minus k, where k is the limit. We must consider a very large positive and a very large negative value of x to do this. So, example 4. Determine the equations of any horizontal asymptotes of this function here, f at x, 3x plus 5 over 2x minus 1, and state whether the graph approaches the asymptote from above or below. So, we can go ahead and factor out the x's. So, 3x plus 5, we're going to factor out the x's. And then we have 2x minus 1, factor out the x's. We're given the equation x bracket 3 plus 5 over x over x bracket 2 minus 1 over x. Okay, again, it doesn't actually matter if you divide the numerator by 3x and 3x and the denominator by 2x and 2x, as long as you're pulling out or factoring out the largest x value, okay, the largest variable. So let's do the limit as x approaches negative infinity. Okay, so these x's cancel out, and now we have 3 plus 5 over x over 2 minus 1 over x. Okay, we're also at the same time going to check the limit as x approaches positive infinity of the exact same function. Okay, so when we sub in negative infinity, we get 3 plus 5 over negative infinity over 2 minus 1 over negative infinity. These two tend to 0, and we get 3 over 2. Okay, for the second one, we get 3 plus 5 over infinity over 2 minus 1 over infinity. These two tend to 0, and we get 3 over 2. So we can conclude that there's a horizontal asymptote at x equals 3 over 2. So when we're testing values to see whether or not we approach from above or below, we have to do this in the advanced functions approach. So let's make a chart here. So there's going to be 3 columns, okay? This is as x approaches. So we're going to test 2 things, as x approaches infinity and x approaches negative infinity, okay? What we're going to do is we're going to sub in a really big number and a really small number for f at x. So for example, we're going to sub in f at 1000, and we get 1.503. And we're going to sub in f at negative 1000, and we're going to get 1.497. The 1000 is representing a very big number, so it's representing infinity. The negative 1000 is representing negative infinity. So this is what we do. We now take a look at 1.503 and 1.497, and we determine how that approaches. X equals 3 over 2. Okay, remember, x equals 3 over 2 is just like saying x equals 1.5. So all we're going to do is we're going to compare these numbers. Is 1.503 higher on the y-axis or lower on the y-axis than 1.5? Well, it's higher. That's a bigger number. So this lies above. This approaches from above. And 1.497 is a smaller number than 1.5. So that approaches from below. So if we have 3 over 2 here, where we can put our arrows, so as x approaches infinity, we're above that line. And as x approaches negative infinity, which is over here, right? Infinity, negative infinity, we are below that line. Example 5. So let's bring this together. For the function f at x equals 3x over x squared minus x minus 6, determine the equations of all horizontal or vertical asymptotes. And then we're going to sketch the graph. Okay? It should be maybe and. Okay. So the denominator. First, let's factor the denominator. What two numbers multiply to negative 6 add to negative 1? Well, it is, we can have 1 and 6 or 3 and 2. Okay, so we get negative 3, positive 2. So we have f at x equals 3x over x minus 3, x plus 2. Okay, so the vertical asymptotes are x equals 3 and negative 2. So let's start with this first, okay? What we want to put down the left column is the 2 vertical asymptotes and how we're going to approach them. So this is going to be x approaches. So x approaches positive 3. Oh, yeah, that's fine. From the left side. And then we have to find when x approaches 3 from the right side. And then we're going to find x approaches negative 2 from the left and x approaches negative 2 from the right. Okay, and what we want to do at the top is we want to put basically all of f at x. So by putting the factors, we can simply multiply all of the signs, and then we can just focus on signs. So in the numerator, we have a 3x, and in the denominator, we have an x minus 3, and in the denominator, we have an x plus 2. Okay, and then this is going to be our overall f at x. So what number is on the left side of 3? We're going to sub in like a 2.9. What number is on the right side of 3? We can sub in a 3.1. What number is on the left side of -2? Maybe -2.1. And the right side of -2, -1.9. Okay, so if we subbed in 2.9, okay, 3 times 2.9 is positive. 2.9 minus 3 is negative. 2.9 plus 2 is positive. Overall, this is negative. Okay, what about 3.1? 3.1 times 3 is positive. 3.1 minus 3 is positive. And then plus 2 is positive. Overall, that one's positive. Okay, negative 2.1 times 3 is negative. Minus anything is negative, and then plus 2 is still going to be negative. That's going to be negative. And negative 1.9 times 3 is negative. Minus anything is going to still be negative. And then plus 2 is positive. So that one's positive. Okay? So since f at x, since the sign is negative, we want to know, where does f at x approach? Well, then it's going to approach negative infinity. Since it's positive, it's approaching positive infinity. Like, these go hand in hand. Okay, negative infinity, positive infinity. Right, because it's positive. Okay. So what we can do, if we want, we can start this graph. And we can draw vertical asymptotes at 3 and -2. Okay, and then what we will do is we'll say, okay, x approaches 3 on the left side toward negative infinity. So 3 on the left side, we're approaching this vertical asymptote going down. And 3 on the right side, we're approaching going up. -2 on the left side, we're approaching negative infinity. And -2 on the right side, we're approaching positive infinity. Okay, so vertical asymptotes are done. Now let's do horizontal asymptotes. Okay, so for the horizontal asymptote, we're going to go f at x equals, what we're going to do is we're going to factor out an x in the numerator and an x squared in the denominator. So we had 3x, so let's divide by x. And then we had x squared minus x minus 6. So x squared minus x minus 6. And we're going to divide all of these by an x squared. Okay, so the function that we're working with is x bracket 3, and then x squared bracket 1 minus 1 over x minus 6 over x squared. And for the horizontal asymptote, we have to determine whether it approaches positive infinity and negative infinity. Okay, so let's go ahead and break this into two. The limit as x approaches negative infinity. And then we're going to do the limit as x approaches infinity. Okay, we can get rid of this x and get rid of this squared. Okay, and we're left with 3 over 1 minus 1 over x minus 6 over x squared. And I'm just going to repeat that. 1 over x minus 6 over x squared. Okay, there's an x in front. So when we go ahead and sub in, we get 3 over x bracket 1 minus 1 over negative infinity minus 6 over negative infinity squared. Both of these will tend to 0. And then this x is also negative infinity. So we get 3 over negative infinity, which is just 0. Okay, and the same thing for the second one. We get 3 over infinity, 1 minus 1 over infinity, minus 6 over infinity squared. Both of these will tend to 0, so we get 3 over infinity, which is 0. So the horizontal asymptote is x equals 0. Okay, now let's test if these approach from above or below. So we're going to test as x approaches negative infinity and as x approaches infinity. So we are going to sub in f at negative 1,000 and f at 1,000. Okay, so we get 0.003. Okay, and then we get negative 0.003. Okay, so now we have to talk about whether this approaches x equals 0 from above or below. Well, 0.003 is a number above 0, and negative 0.003 is below 0. So, as x approaches negative infinity, we're going above. So come back up here to the graph. X approaches negative infinity, we're approaching from above. And as x approaches positive infinity, sorry, this is negative, this is positive. So this is below and this is above. So delete this. And this is going to be below as we approach negative infinity. And this is going to approach above as we approach infinity. Right. Horizontal asymptotes and limits at infinity. So if the limit of f at x as x approaches infinity equals L, so some number, or the limit of f at x as x approaches negative infinity, also some number, we say that the line y equals L is the horizontal asymptote of the graph. Okay, so we kind of already talked about this. Okay, this would be L, and we could either approach from above or below. Okay, so if f at x is greater than L, so this is our testing chart, right? So if our function, when we plug in like a really big number, is greater than the limit, the graph approaches from above. And if the number that when we plug it in is less than the limit, then the graph approaches from below. Okay, so right now we're going to transition into oblique asymptotes. These are lines that are slanted, so they're not vertical, they're not horizontal, so they're not those asymptotes like that we've focused on so far. Okay, and that line that's slanted, the curve becomes increasingly close to it. So again, is an oblique asymptote. These occur with rational functions when the degree in the numerator is one more than the degree in the denominator. So, if we take a look at example 6, determine the equations of all asymptotes of this graph here. Okay, so f of x equals 2x squared plus 3x minus 1 over x plus 1. So if we're taking a look at the vertical asymptotes, the vertical asymptote is x equals negative 1, and then we can do a chart. But when we take a look at the horizontal asymptote, let's do f at x equals, okay, we have 2x squared plus 3x minus 1. Okay, so let's go ahead and divide out that 2x squared, the full coefficient. Okay, and then that's over x plus 1. So let's go ahead and divide out by that first full coefficient. Okay, so we would rewrite the factor 2x squared, and in the brackets we would have 1 plus 3 over 2x minus 1 over 2x squared, all over x, bracket 1 plus 1 over x. Okay, at this point we take a look at the factors, and there's 2x squared and then there's x in the denominator, and we can go ahead and cancel those out. So now when we transition into just working with the equation, okay, into the limit, we can do the limit as x approaches infinity of 2x, 1 plus 3 over 2x minus 1 over 2x squared, all over 1 plus 1 over x. And we can go ahead and sub in this infinity okay, and here, so when we sub in infinity, we get 2 infinity, and then 1 plus 3 over 2 times infinity minus 1 over 2 times infinity, all over 1 plus 1 over infinity. Okay, so when we think about this, 3 over a big number goes to 0, negative 1 over 2 times a big number goes to 0, and 1 over infinity goes to 0. So the limit as x approaches infinity of f at x is going to equal, well, there's 2 times infinity over 1. So it's essentially infinity. Okay, so we haven't seen this yet. What does this mean? Therefore, the limit does not exist. So the limit does not exist. And with this logic, the limit of, actually I'm going to put this together, x approaches negative infinity does not exist for the same logic. So what we want to do instead is, because the numerator, the degree in the numerator is 1 more than the degree in the denominator, what we want to do is divide the numerator by the denominator. Okay, so for the numerator, we can do long division, or we can do synthetic. Let's go ahead and, I feel like it's a quick one, so let's just do long division. Okay, so 2x squared plus 3x minus 1 divided by x plus 1. So what number times x will give us 2x squared? Because this is our focus, okay, this is our goal, and it's going to be 2x. So now let's finish it. 2x times 1 is 2x. And then we put this expression in brackets and we subtract them. Okay, so 2x squared minus 2x squared goes away. This goes to 0. 3x minus 2x is just x. And then minus 1. Okay, so we think, what times x is going to give us x? Well, just 1. So we put 1 in here, plus 1. And 1 times x is x. 1 times 1 is 1. Okay, so let's group these as a binomial and subtract. X minus x goes away, and negative 1 minus 1 is negative 2. That's going to be the remainder. Okay, so if you think about this, f at x equals 2x plus 1, right, minus 2 over 1 plus x plus 1. Okay, we can rewrite this equation like this, and they're equivalent. So taking this right here, what we found, this is going to be the oblique asymptote. Y equals 2x plus 1. If you're thinking, what's that even look like? Well, on a curve, plus 1 is going to be your y-intercept, and 2 is going to be your slope. So it's going to be positive, and it's going to raise to the right. Okay, so instead of doing that, I'm going to do this with a dotted line because it's an asymptote. And then I'm going to do the vertical asymptote of x equals negative 1. and this is y equals 2x plus 1. And those are going to be our two asymptotes. Okay, so going back up to the question, determine the equations of all asymptotes of the graph. Okay, let's just say, therefore, VA equals x equals -1, and oblique asymptote is y equals 2x plus 1. And we say no horizontal asymptote.